Welcome to our lecture video in hydraulics under the topic Fluid Flow Measurement Falling Head Orifice. Now in this video, we will answer the 3 examples in the handout, and this is our first example. A circular vessel 2 meters in diameter and 4.5 meters high as shown is filled with liquids A, B, and C respectively. At the bottom of the vessel is a 0.09 meters squared standard orifice. If C, or the coefficient of discharge, is 0.60, find time to remove letter A, liquid A out of the container, letter B, liquid B out of the container after liquid A is removed, and letter C, time to empty the container. So we have this container here. So we have our liquid A being at the bottom because of the specific gravity is higher compared with the liquids B and C, and the heights are given as 2 meters, 1.5 meters, and 1 meter. The diameter here is 2 meters. So the diameter here is 2 meters. Okay, so find the time T to remove liquid A, this liquid here, out of the container. So our formula for that, for time T, given uniform area wherein as time changes, or as the fluid goes down, so as the fluid goes down here, the surface area does not change. So if that is the case, if the surface area does not change as time changes, therefore we will use the formula time to remove a liquid, and in this case liquid A, is equal to 2 times the area of the surface, the water surface, multiplied with the square root of the initial height of that liquid minus the final height of the liquid. That is all over the coefficient of discharge multiplied with the area of the orifice, then square root of twice the gravity. So this is the formula when we are dealing with the surface does not change. When the water surface, the area of the water surface does not change. Okay, so but how do we deal with a container or this vessel containing different kinds of liquid? So we need first to make it uniform. So we will convert the system into a singular liquid. So we will convert it into singular liquid A. So how do we do that? So the pressure here at the bottom, so pressure original is equal to the pressure wherein we are going to have singular liquid. So say nu, okay, pressure nu. So the pressure nu, let's exchange that. So P1, let's just say P1, P2, having the P1 as the new pressure wherein we are having one liquid only, and P2 is the original pressure. So for P1, which is we are going to convert it into this, so gamma HA. So gamma HA, being the gamma here is the gamma of the liquid. Of course, we have the specific gravity since they have different specific gravity, A. Then we have here a specific gravity B, or that is equivalent to specific gravity A, gamma, HA, plus specific gravity, oh no, this is different, so this should be different. It should be H, the new one, let's say H1. Okay, H1. We will be looking for the H1 of the liquid A. So SG B gamma H HB. Okay. Our gamma here being the gamma of water. So gamma of water, gamma of water, gamma of water, plus SGC, gamma of water, HC. So cancel all gamma of water, we'll cancel that out. So what's left here is the S specific gravity at A, which is 1.05 H1, is equal to the specific gravity of A, 1.05. The height there is 1, so its height is 1, plus specific gravity of B is 0.9. The height of B is 1.5. Then plus specific gravity of C is 0.8, and the height of C is 2 meters. So we now have the equivalent height is equal to, this is H, or let's just say equivalent. So equivalent, so height equivalent. And then let's just name this P2 here as the original pressure. So yeah. So we now have here 1.05 plus 1.5 times 0.9 plus 0.8 times 2 divided by 1.05. So that is 3.81 equivalent height. So 3.81 meter equivalent height of A. Now, since we are to remove, liquid A, so that means it looks like this. So this now looks like, so we'll put it here. We now have here the total height now. Our HE is equal to 3.81 meters of liquid A, and the pressure here is the same. The pressure at the bottom, the pressure original, is the same pressure as the equivalent here, or the equivalency. So since we are going to remove 1 meter of liquid A, so we are removing 1 meter of liquid A. So that means this is our H1. So this becomes our H1. Or, yeah. So let's just say H1 here. So if we remove 1 meter here, what height of the liquid remaining? If you remove 1 meter of the liquid A, so if you remove the 1 meter of liquid A here, what's left will be because our H1 here is actually this one. This is our H1, original height. H2 is 3.81. That will be minus 1, so 2.81 meter. Okay. Therefore, our time T from our formula here, our time T now, so let's see if we can put it here. There. Time A is equal to 2 times the surface area. The surface area is pi over 4 times the diameter is 2 meters squared times square root of the, what's our H1? Our H1 is 3.81 minus the square root of here our H2, that will be 2.81 over our C. So what's our coefficient of discharge? We have 0.6 times the area of the orifice. The area of the orifice here is, it says here at the bottom of the vessel is a 0.09 meters squared. So it's already area here. So area of the orifice there is 0.09 meter squared. Then we have there square root of 2g, square root of 2g, twice of gravitational acceleration. So our time A now is 2 times shift pi over 4 times 2 squared times square root of 3.81 minus square root of 2.81 over 0.6 times 0.09 square root of 2 times 9.81. So 7.24 seconds. So time to remove A is 7.24 seconds. So time A. That's for letter A. Okay. Now for letter B, time to remove liquid B out of the container after liquid A is removed. So after liquid A has been removed, how long will liquid B be emptied? So that means, so it will just look like this. So this is our container. That's what's left on the container. So again, just like what we did here in liquid A, we need to find the equivalent height when we are dealing with one liquid only. So what is the equivalent height here of liquid B? So this has pressure at the bottom. So again, that is pressure original, or we have equivalent pressure original is equal. So they are equal. For the pressure equivalent, we have there the specific gravity of B, gamma of water, then the height of B equals the original pressure here. So we have specific gravity of, this is height of equivalent height. And then we have a specific gravity of B, gamma of water, height of B, plus a specific gravity of C, gamma of water, height of C. So cancel water, gamma of water. A specific gravity of B is 0.9 times the HE equals specific gravity of B, 0.9. The height is 1.5 plus specific gravity of C is 0.8, height is 2 meters. So what is now the equivalent height if we are considering only liquid B? So that will be equal to 0.9 times 1.5 plus 0.8 times 2 all over 0.9. So 3.28 meters. 3.28 meters. So that is the equivalent height. So that's the equivalent height of B here. So that is 3.28. Now if we remove 1.5 of B out of this container here, out of this equivalent height here, what is left of, what's the left height? So H1 is 3.28 meters. So while H2, the final height after this liquid of 1.5 is removed, that would be 3.28 minus 1.5, and that is equal to 1.78. 1.78 meter. Therefore, time to remove liquid B is equal to 2 times the surface area, diameter 2 meters squared, square root of the initial height, which is the equivalent height of 3.28 minus the height after 1.5 is removed, all over the coefficient of discharge 0.6, the area of the orifice 0.09, and square root of 2 times the gravitational acceleration. So what is now time to remove B? So cancel 4. So 2 times pi square root of 3.28 minus square root of 1.78 all over 0.6 times 0.09 square root of 2 times the accelerational gravitation. So 12.53 seconds. So 12.53 seconds. Time to remove liquid B after liquid A has been removed. Now let's go to liquid C, or problem C. Time to empty the container. So obviously for liquid C, what we have left here, so there is no more looking for the equivalent H because we only have liquid C left. So here is our liquid C of 0.8 specific gravity, 2 meters high, we have 2 meters diameter. Okay, so time to remove, total time is equal to time to remove A plus time to remove B plus time to remove C. So we're looking for time to remove C. So time to remove liquid C is equal to 2 times the surface area of the this container here, the water, squared, times square root of the initial height is 2 meters, the height here is 2 meters, minus the final height, that will be 0 because it's already empty. Then C, coefficient of discharge, times area of the orifice, square root of twice of gravity, or gravitational acceleration. So time C is equal to square root of 2.6.09 square root of 2 times 9.81. So So 37.15 seconds. So 37.15 seconds. So time total is now equal to 7.24 plus 12.53 plus 37.15. Time total now is equal to 7.24 plus 12.53 plus 37.15. So 56.92 seconds. So 56.92 seconds. Here, that's the final answer. So that's for number 1. Let's go to number 2. A composite non-prismatic 5 meters high cylindrical tank has the form of a frustum of a cone at the bottom with a 2.5 meters diameter uppermost and 1.25 meter diameter at the bottom and 4 meters high. The bottom contains 100 millimeters diameter orifice with coefficient of discharge of 0.60. Letter A, if fully filled with water to the top, determine the time to remove the capacity of the cylindrical tank. So, here is our container. So, for letter B, determine the time to remove all the liquid at the frustum of the cone only when it was initially full of water. And letter C, determine the time to empty the composite tank in minutes when it was initially full. Okay, so this is our composite non-prismatic cylindrical tank and has a frustum of a cone, so this one here, at the bottom, and it is filled with liquid and it's filled with water up to the top. And this is 5 meters high cylindrical tank, 5 meters high cylindrical tank, and then 4 meters high frustum of a cone. Okay, so having the diameter at the uppermost, 2.5 meter diameter uppermost and 1.25 meter diameter at the bottom. So that is 2.5 meters diameter at the top, and we have here 1.25 meter diameter at the bottom. So for letter A, if it is fully filled with water to the top, so we have water up to the top here. So we have our water here, the top. Determine the time to remove the capacity of the cylindrical tank. So this is our cylindrical tank and we are to remove it. So from here, we will remove the up to this point. Okay. So from this point at the top, and then the water will flow out of this cylindrical container up to this point. So therefore, what is now our H1 and H2? So our H1 will be, for letter A, our initial height is 9 meters and our final height after removing the water from the cylindrical tank, so that is equal to 4 meters. So our datum line is here. So this is our 4 meters and this is our 9 meters. So time to remove the water from the cylindrical tank. So this is our cylinder, volume frustum of a cone. So that is equal to twice of the area of the surface times square root of H1 minus square root of H2. Then C, coefficient of discharge times area of the orifice, square root of twice of gravity. So that's our formula. So our surface area is pi over 4. Our diameter is 2.5 squared times square root of 9 minus square root of 4 all over 0.6 times the area of the orifice. The area of the orifice is pi over 4. Diameter of the orifice is, where is the diameter? It's 100 mm diameter orifice. So 100, that is 0.1 meter squared, square root of twice of gravitational acceleration. So time to empty the cylindrical container is equal to, cancel pi over 4 here. So 2 times 2.5 squared times square root of 9 minus square root of 4. 0.6 times 0.1 squared, square root of 2 times 9.81. So 470.34 seconds. So that is 470.34 seconds. So that is the answer for letter A. Now for letter B, it says there, determine the time to remove all the liquid at the frustum of the cone only when it was initially full of water. So again, the water here is initially full. So the water is initially full, and then we will need to remove only the water at the frustum of a cone. So if that happens, where will the water level be? So here is our container. So what will happen here? Okay, so this is our frustum of a cone. So this is our water surface. So from here, the water surface, and then you will be removing this, the volume of water at the cone. So obviously it will not go here because the volume of the frustum of a cone is smaller compared with the volume here at the cylinder. So what will happen to the level of the water surface here? It will not go here lower than the frustum of the cone, or it will not go to the frustum of a cone, but rather the level of water stays here somewhere in the cylindrical tank. So let's assume that it's contained here. It's here. There. The level of the water is there. So it's not totally here, but rather it's somewhere here in the cylindrical tank. So how do we solve here? The challenge here is looking for the value of H2 because we need to find out. So having known our value of H1 as this, obviously that is 9. This is our H1 is equal to 9 Now, the question here is, what is the value for H2? So, this H2 here. Question mark. So, we know that this is 4 meters. This part here is 4 meters. So, how about this part here? What is the value of H here? So, let's look for the value here. This is our H. So, we need to determine what is the volume remained. This is our volume of the frustum of the cone. So, we need to find out what is our volume remained. So, let's have VR here as the volume remaining. And that is equal to, so our volume remaining VR is equal to pi r squared H. So, this is our H here. So, this is our radius. So, this is our radius. This is our radius here. So, this is 2.5 divided by 2, 1.25 meter. This is our big radius. So our smaller radius here R is equal to, that is 1.25. So 1.25 diameter divided by 2, that is 0.625. So that is the radius. So how do we solve for the value for VR? For H, we're looking for the value of H here. Because H2 is equal to H plus 4. Right? So VR is this one. And also VR is also volume of the cylinder minus the volume of the frustum of a cone. Why? Why is that? Because, yes, the reason why this is VCY or volume cylinder minus the volume of the frustum is that the liquid here, that the volume of the water here is actually that's actually the volume of the cylinder. So after removing, so it's like after removing the volume of the frustum here, what's left is the volume of the cylinder, and it goes down. The water of the cylinder goes down. That's why it looks like this. Okay? So removing the volume of the frustum, so this is what's left. Therefore, volume of the cylinder minus the volume of the frustum is equal to the VR or the volume remained here. So that's what happened here. So what is the volume of the cylinder? Volume of the cylinder is equal to pi over 4 times the diameter 2.5 squared times the height of 5 meters. So that is equal to shift pi over 4 times 2.5 squared times 5. So 24.54. So 24.54 cubic meter. And then volume of the frustum of a cone is equal to pi h over 3 times small r plus small r squared plus big R squared plus r. So that's the formula for volume of the frustum of a cone. So VF is equal to pi h. So our h here is 4 meters divided by 3. So our r here is, small r is 0.625 squared plus our r. So there we go. Our r, bigger r here is 1.25 and plus 0.625 times 1.25. So volume, the frustum of the cone now is equal to 0.625 squared plus 1.25 squared plus 0.625 1.25. So 11.45. So 11.45 cubic meter. Therefore, our VR now is equal to VCY of 24.54 minus 11.45. That is equal to 24.54 minus 11.45, 13.09. So 13.09 cubic meter. So using this volume, we can now solve for the h of this. So 13.09 is equal to pi r. Our r is 1.25 squared h. So what's the value for h? 13.09 shift pi times 1.25 squared. So 2.67. H is 2.67. Therefore, we now have the value for H2. The H2, the level of water at this point. We now have our H2. So therefore, H2 is equal to 2.67 plus 4. H2 is equal to 6.67. We can now solve for the time to remove the water at the frustum of the cone. So TF is now equal to 2 times the surface area pi over 4, the area, so diameter pi d, times square root of the initial height 9 and then the final height of 6.67 all over 0.6 for the coefficient of discharge pi over 4, area of the orifice, so the diameter is 0.1 squared, square root of 2 times the gravitational acceleration. So time to remove water at the frustum of the cone is now equal to, cancel, pi over 4 square root of 9 minus square root of 6.67, 0.6 times 0.1 squared, square root of 2 times 9.81. So 159, 2 times of 2.1 So it's 2.5. Okay. So 196.30 seconds. So this is our answer. That's for letter B. Next, what's on letter C? Determine the time to empty the composite tank in minutes when it was initially full. So we're looking for the total time. So we should not use TF here because we're not totally just removing the frustum of the cone. Let's just say time T. Okay, let's just say time T there. Because for letter C, we need to determine the time to empty the composite tank in minutes. We need to find time to remove the cylinder plus time to remove the frustum of the water at the frustum of the cone. So we need to find the value for TF because TCY is already found. We have 470.34 seconds. So solve for TF. The time to remove the water here, the frustum of the tank. To empty the composite tank in minutes when it was initially full. So we remove the scenario here is like this. So first we remove the liquid or the water from the cylinder. So from this initial location from 9 meter high goes down to the 4 meters high. So this is our TCY. So we got the time and that is TCY. Now the next scenario is having this water level here go down to the frustum of the cone up to the level wherein the final height is 0. Okay, so from the initial height 4 meters down to the final height of 0 meters. Now here is the challenge here. The challenge here is that the surface area is no longer uniform. So unlike what we did with the water level while it's still in the cylinder, the water level in the cylinder here has a uniform surface area. It's the same surface area. But when it reached the location here at the frustum of the cone, the surface area changes. How do we solve for time when the surface area is changing? So that is our situation C. So the surface area here is changing. So we will need to solve here using integration. So we will integrate this solution here because as you can see it will change. So we will get here so let's put the level here of the water. So this is our strip, our area strip. So solving for the integration here. What's the formula for integration? Because we will be looking for time, total time here is equal to time to remove the water from the cylinder, which we already have, plus time to remove the water at the frustum of the cone. wherein our time for the frustum of the cone is the integral of the area surface, the surface area over the all over the coefficient of discharge times the area of the orifice square root of 2gh. So this is the formula, and that is from initial height to the so we will change that from the final to the initial. Okay, so this is our formula. This is the formula that we are going to use. Oops. So take note that take note here that this is H2 and this is H1, and remember that our H1 or initial height is higher compared with our final height, so our final height here is lower. So what we're going to do here is that our TF is equal to integral of the area of the surface, which is, this is our challenge because it's changing, right? So it is changing, and then we need to put something variable here in order to solve for AH. This is what we're going to do here. So we need to find or to get a to convert. We need to convert this ES into something integratable. We could integrate. So we need to find ES in terms of H. So we will use H here. So let's put our H at the top, H negative 1/2 dH all over CAO square root of 2G. Then from 0 to 4. So that is, so we will need to find ES. So let's work on this portion here. So this is the radius. This is our 1.25 meter radius at the top. This is our 0.625 radius at the bottom. Okay. Then this is our height. This is 4 meters. And this is, let's name this as H, which is changing. So this is our level of water, which is changing. And if this H is changing, because as time passes by, due to the presence of the orifice at the bottom, so the water goes out from the container, and as the surface goes down, H goes down, and the radius is also going to get smaller. So our radius, we need to find the value for radius. So we can use actually here a ratio and proportion. So I'm looking at a ratio and proportion possibility here. So we can do that. We can do a ratio and proportion here. Since this is 0.625, so we can expect that this is 0.625. And therefore, 1.25 minus 0.625 is also 0.625 here. So 0.625 here for the base of our triangle here. And we're looking for the radius. So since we're looking for the radius here, so might as well look for the value of x here. So this is the radius that we're looking for. And this is our x for this triangle here. So there is triangle here and another triangle there. So it's a similar triangle theorem. So by ratio and proportion, we have 0.625 here. This is our x for the water surface. Let's color that blue. Okay. And then this is our 4 meters and this is our h. So by ratio and proportion, this is x over h equals 0.625 all over 4. Therefore, x is equal to 0.625 divided by 4, 0.156 each, 0.156 each. Therefore, our r here, r is equal to 0.625 plus x is actually r is equal to 0.625 plus 0.156 each. So we now have r here in terms of h, and we can use this in our formula here. So finally, we can integrate this one. So our r is used in the area of the surface, which is pi r squared. So the area of this surface here is pi r squared. So that is area of the surface is equal to pi. Our r is 0.625 plus 0.156h squared. And we will substitute this here in our formula. So TF now here is equal to integral of so that becomes pi times 0.625 plus 0.156h squared, h negative 1/2 dh all over c of 0.6 times the area of the orifice of pi over 4, then 0.1 squared, square root of 2 times 9.81. So from 0 to 4. So TF now is equal to, so let's cancel pi here. So that is 4. Let's reduce this one. 4.6 times 0.1 squared, square root of 2 times 9.81. So 150.51. So this becomes 150.51 integral of 0 to 4. So integral of this is square here, that is 0.625 squared, 0.391, 0.391 plus 0.156 times 0.625 times 2, 0.195 each plus 0.156 squared 0.024 h squared h negative 1/2 dh. So that is equal to 150.51 integral of 0 to 4, that is 0.391 h raised to negative 1/2 plus 0.195 h raised to 1/2 plus 0.024 h raised to 3/2 dh. So we can actually have the value of TF already here. If you have a good calculator there. So 150.51 integral of 0.391 alpha x raised to negative 0.5 and 0.195 alpha x raised to 0.5 plus there plus 0.024 alpha x raised to 1.5, and that is from 0 to 4. That is 438.165. 438 is 438.165 seconds. So that is the answer. But what if your calculator cannot process this one here? What if it can't be processed? So we can have the longer method. So we integrate. So 150.51. So we will find the integral of this one. That becomes 0.391 h raised to 1/2 all over 1/2, right? So if you should recall your integration. So why it happened? It's because we have integrated it. So 195 h raised to 3/2 and plus. So I suggest you review integration in order to understand what happened here in the longer method. 5/2. Then we have here from 0 to 4. So all we need to do here is to substitute h here. We substitute the h here. We will substitute the 4 into the h here. So 150.51. So 0.391 times 4 raised to 1/2 over 1/2 plus 0.195 times 4 raised to 3/2 over 3/2 plus 0.024 4 raised to 5/2 5/2. So calculator. Now this is the longer version. So this is 2 times 0.391 4 raised to 0.5 plus 2 times 0.195 times 4 raised to 1.5 all over 3 plus this is 2 times 0.024 times 4 raised to 5 over 2 all over 5. So there, the answer here is 438.165. So it's the same answer. So this is the answer I know, not yet. This is just TF. So therefore, our time total is equal to the cylinder, which is 470.34 plus 438.165, and that is equal to, so 470.34 plus 438.165, 908.505. So 908.505 seconds. But in the problem, it wants minute. So how many time in minute? So in 1 minute, we have 60 seconds. So cancel second there. So 90. So the answer divided by 60 is 15.14 minute. So 15.14 minutes. So this is the answer. So that's for number 2. Let's go to the last example. A prismatic vessel has two compartments, A and B, connected by an orifice 0.3 meters square, as shown in the figure. At a certain time, the water in A is 6 meters above the center of the orifice, and in B is 3 meters. Compute letter A, discharge from A to B. B, time in which the water surfaces in the two tanks will reach the same level. C, how soon thereafter will the water surface be 1 meter apart. Okay. Now here is something tricky about this problem here. It's about the orifice. So the orifice is described as 0.3 meter square. It's so easy to mistake this for the area. But actually, this 0.3 meter square here means that the orifice has a square opening of 0.3 by 0.3 meter sides. So it's 0.3 by 0.3 meter. That's the orifice. It's a square orifice given this dimension. So 0.3 meter. Okay. For letter A, discharge from A to B. So we're looking for the discharge. So that is, for letter A, Q is equal to, the formula is Q is equal to the coefficient of discharge it's actually given in the problem, but it's, as I forgot to put here, the coefficient of discharge is actually given. C is equal to 0.6. So C is equal to 0.6 here. So our coefficient of discharge is 0.6. So Q is equal to C, the area of the orifice, and square root of 2gh. So this is the formula. Formula for Q. So that is equal to 0.6 times the area of the orifice is 0.3 squared. Square root of 2 times 9.81, and the difference in elevation. So the difference of elevation of the two water surface here is 3 meters. So let's put here 3. So we now have the value for Q. 0.6 times 0.3 squared times, that is square root of 2 times 9.81 times 3. Oops, times 3. So 0.414, 0.414 cubic meter per second. So that is our Q. And then for letter B, time in which the water surfaces in the two tanks will reach the same level. So it will reach the same level. So this is the condition. So initially, this is our water surfaces. And then it will go at such at time passes by, it will have the same elevation. So it's asking the time in which the water surfaces in the two tanks will reach the same level. So this. So from the initial height, the difference of the height is 3 meters. So this is also our H1. Up to the time we're in, H2 becomes 0. Okay? From H1 to 3 to H2 equals to 0. Meaning, their elevation is the same. So we will use the formula here. Time is equal to twice of the area at A. So this is our A and B. So twice the area at A and at B. So 2A and B times square root of H1 minus square root of H2 over the area at B plus, the area at A plus area at B times the coefficient of discharge times the area of the orifice, square root of twice the gravity. So this is our formula. There. That becomes our formula. So we need to find what's the value for area at A. So area at A is equal to 1/2. So this is our area at A. So as you can see, it's trapezoidal. So we're going to use trapezoidal area. So 1/2, this is 5 plus 4 times the height of 3. So area at B is equal to 1/2 4 plus 3 times 3. So that is equal to 1.5 times 9, 13.5 square meters. And then 10.5 square meters. Therefore, this is now equal to 2 times 13.5 times 10.5 times square root of 3 minus square root of 0 all over 13.5 plus 10.5 times 0.6 times 0.3 squared, then square root of twice of gravity. So time now is equal to, So 2 times 13.5 times 10.5 times square root of 3 and 13.5 plus 10.5 times 0.6 times 0.3 squared, square root of twice of gravitational acceleration. So 85.54 seconds. That's when their elevation becomes equal. Now for letter C, how soon thereafter will the water surface be 1 meter apart? So 1 meter apart. Oops. So let's just draw it. C. So how soon will their water level be 1 meter apart? So this is their initial, let's just exaggerate it a bit, and this is their final. Okay? So from the initial, wherein they are 3 meters apart, so this is their initial difference. There is 3 meters apart, and then to the point wherein they become like this. They are 1 meter apart, and let's name this as X and this height here as Y. Okay? So how do we solve this? We will solve this by the formula time is equal to volume over Q average. So this is our formula. So in this situation, this is what we're going to use. That formula, time is equal to volume over the Q average. So we will need to find first the values of X and Y in order to get the volume. So we're asked for the volume of this, the liquid here, or we can use the liquid here. The change in elevation, and what's that volume there? Okay. So we need to find the value for X and X or Y. Okay. So we know that this condition is from H1 of 3 meters to the condition H2, which is 1 meter. So how do we do that? So X plus 1 plus Y is equal to 3 meters. Therefore, our X here is 2 minus Y. So we will equate here the two volumes. So volume at A, and then this is volume at B. Volume A and B. So volume at A, what happened here at the volume at A, so it also happened here at the volume at B. So that's why they are equal. The area that we solved a while ago at A multiplied with X height, the height here X is the volume at A, and then we have here the area at B multiplied with the height of this volume here, which is Y, becomes the volume B. So this is 13.5. Our X is 2 minus Y equals A. B is 10.5 Y. So we will now have the value for Y here. So that is equal to twice of 13.5 all over 13.5 plus 10.5. Our y is 1.125. So y is 1.125 meter. Therefore, the x becomes 2 minus 1.125. So x, oops, why did I put parenthesis there? It's not. So 2 minus 1.125 is 0.875. 0.875 meter. So we can now solve for the Q Ave is equal to C, or coefficient of discharge, times the area of the orifice, square root of twice of gravity, times square root of H1 plus square root of H2 all over 2. So this is the formula for the Q average. So we have there 0.6 for coefficient of discharge, 0.3 squared for the area of the orifice, twice of the gravity, square root of twice of gravity, times square root of H1, which is 3, plus square root of H2, which is 1, all over 2. So Q average is equal to 0.6 times 0.3 squared, square root of 2 times 9.81 times, oops, times square root of 3 plus square root of 1 divided by 2. So 0.33. So that is 0.33 cubic meter per second. And that's what we are going to use here at the top. So time now is equal to the volume. Our volume is, let's say, volume at A. So 13.5. So our volume A here. And this is our volume. So 13.5 times dx of 0.875 divided by Q Ave of 0.33. So time is now equal to 13.5 times 0.875 all over 0.33. So 35.8 seconds. Or we have another solution there, or time using volume at B. So that is 10.5 times y of 1.125 all over 0.33. So time is are they the same? Let's see. So that is 10.5 times 1.125. Yes, they are the same. Okay, so that's for number 3. So example number 3. Okay, so that's all for this video.